Welcome to the Deep Dive, where we unlock the hidden patterns of our world, one fascinating discovery at a time. Today we're diving into something truly extraordinary, the golden ratio, often called nature's aesthetic blueprint. Thank you so much for joining us on this insightful journey, proudly brought to you by the All Sorts podcast. And honestly, to everyone who has already hit that subscribe button and become such a vital part of our ever-growing community of curious minds, your support is just incredible, and we're so grateful. If you haven't yet, please do join us on YouTube to uncover more remarkable stories like this one. And hey, be sure to follow us on X, Instagram, and Threads too. Here, we really try to distill the most intriguing insights from diverse sources, turning complex ideas into, well, hopefully captivating conversations. For this deep dive, we're drawing from some great stuff. Beauty in mathematics, examples of the golden ratio you can find in nature, and some pretty groundbreaking studies on human skull dimensions.
Yeah, this exploration promises to be a remarkable one. As we sort of peel back the layers, we'll see how a single, really elegant mathematical constant seems to underpin both the breathtaking beauty and the astonishing efficiency found right across living systems and even human creations. It's really a profound testament to the deep, often unseen connection between numbers and the very fabric of the world around us.
Okay, let's dig into this right from the start. What exactly is the golden ratio? You often see it represented by the Greek letter phi.
Right, it's right, phi. And at its core, it's a way of dividing a line segment. Imagine you have a line and you split it into two unequal parts. The golden ratio is the point where the ratio of the whole segment to the longer part is exactly the same as the ratio of the longer part to the shorter part. It's this unique point of balance, you could say.
A kind of perfect proportional split. And it has a number, right? Like pi.
It does. Its approximate numerical value is 1.618803, and that 3 is important.
Right.
Because, like pi, phi is an irrational number. That means its decimal representation goes on forever without repeating. It's infinite non-repeating. But what makes it, well, truly captivating for many is its incredibly close connection to the Fibonacci sequence.
Yes, Fibonacci. I remember that from school. 0, 1, 1, 2, 3, 5, 8.
Exactly. Each number is just the sum of the two before it. So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on forever. Now, here's the magic, the really cool part. As the sequence progresses, if you take the ratio of any number to the one just before it, say, 34 divided by 21, or 144 divided by 89, that ratio gets closer and closer and closer to phi, to 1.618. It asymptotically converges, is the mathematical term. It creeps infinitely close, but never quite gets there.
Wow. And this isn't some, modern math thing, is it? I feel like I've heard it goes way back.
Oh, way back. Its origins stretch deep into antiquity. You've got Pythagoras back in the 6th century BC, who's often credited with discovering irrational numbers and maybe even recognizing this special ratio. Then fast forward a bit to around 300 BC, and you have Euclid of Alexandria, the father of geometry himself. He gave us the first known written geometric description in his famous book, Elements. He didn't call it golden, though.
No, what did he call it?
He called it being cut in extreme and mean ratio. Not quite as catchy, perhaps.
No. Not really. So when did golden ratio come about?
Well, the term golden ratio itself seems to have gained traction much later, possibly popularized by Leonardo da Vinci during the Renaissance. He wasn't just an artist, he was fascinated by proportion. He subtly incorporated these proportions into masterpieces like the Annunciation, and he actually illustrated Luca Pacioli's big book on the topic, De Divina Proportione, which translates to On the Divine Proportion.
Divine proportion. That definitely sounds more impressive.
It certainly does. But even before Da Vinci and Pacioli, you see hints of its practical use. Think ancient Egypt, Babylon, the construction of the pyramids, for instance. Some analyses suggest those builders might have intuitively, or perhaps deliberately, used these proportions for structural and aesthetic balance. It connects to what the mathematician Hermann Weyl said about symmetry being the idea by which man for centuries tried to comprehend and create order, beauty, and perfection. The golden ratio is a profound example of that kind of inherent symmetry.
Okay, this is where, for me, it gets really interesting. Moving beyond the math books and the art history. Because this ratio and Fibonacci, they aren't just human ideas, are they? They seem to be, woven right into nature itself.
That's exactly right. It's almost ubiquitous once you start looking. We find examples pretty much everywhere, from the tiniest plant structures to, well, potentially the shape of galaxies. It does feel like nature leans on this pattern.
So give us some examples. Where does it show up?
Well, a really common one is in flower petals. If you actually go out and count the petals on different types of flowers, you'll often find the number is a Fibonacci number. Think of lilies with 3 petals, buttercups usually have 5, some delphiniums have 8, chicory often has 21, and daisies. Well, daisies frequently land on 34 or 55 petals. It's called Fibonacci phyllotaxy.
Oh, taxi. Okay. So it's not just random.
Doesn't seem to be, no. It appears to be nature's way of ensuring things like structural integrity or maybe maximizing sun exposure for the petals.
And I've heard about it in seeds, too, like sunflowers.
Yes, sunflowers are a classic example. Look closely at the head of a sunflower. You'll see those seeds arranged in spirals, right?
Yeah, definite spirals.
Okay, now count the spirals going clockwise and then count them going counterclockwise. Very often you'll find that those two numbers are consecutive Fibonacci numbers, like maybe 34 spirals one way and 55 the other, or 55 and 89 in larger sunflowers.
Wow. Why would nature do that? It's thought to be an incredibly efficient packing strategy. It minimizes wasted space, ensures each seed gets the resources it needs, maximizes things like light exposure or access for pollinators. It's really elegant engineering. You see similar spirals in pineapples, pine cones, even cauliflower.
Cauliflower.
Yeah.
Okay, I'll have to look closer next time. What about bigger structures, like trees?
Absolutely. Fibonacci numbers often pop up in the way trees branch. You know how one trunk splits into branches, which then split again, or sometimes in the number of leaves on a stem section. And there's something called the golden angle, which is derived from phi, roughly 137.5 degrees. This angle seems to be optimal for arranging leaves around a stem. It ensures new leaves emerge in the spot with the most open space, maximizing sunlight exposure and minimizing overlap. It's quite ingenious.
Nature optimizing again. So plants seem full of it.
Yeah.
What about us? Animals, humans. I know there are claims about the human body.
Yes, that's a long-standing idea, and it's sometimes a bit controversial or hard to pin down precisely. Adolf Zeising, back in the 1850s, was a big proponent, arguing the golden ratio was a universal key. He suggested the navel divides the human body height according to this ratio. People also point to proportions in the hand, the length of the finger bones, and in the face, the positioning of the mouth and nose relative to the eyes and chin. Animal bodies sometimes show tendencies too, like, often having 5 appendages on the torso, 5 digits per limb, 5 facial openings, 5 being a Fibonacci number.
Interesting. And those beautiful spirals in shells like the nautilus, are those perfect golden spirals?
Ah, the nautilus. It certainly looks like a perfect logarithmic spiral, which is mathematically related to phi. And you see similar graceful spirals in things like the cochlea of our inner ear, the horns of some animals, even spider webs. And scaling up massively, spiral galaxies like our own Milky Way show these incredible swirling arms. Even hurricanes can take on that shape.
It's just staggering how it appears at so many different scales. Does it go even smaller, like right down to the molecular level?
It appears so, yeah. Even the blueprint of life itself, the DNA double helix, each full cycle, each complete turn of that spiral measures approximately 34 angstroms long and 21 angstroms wide.
Wait, 34 and 21?
Exactly. Consecutive Fibonacci numbers. Their ratio, 34 divided by 21, is about 1.619, which is incredibly close to Phi, 1.618. So yeah, the very code that builds us seems to echo this ratio.
Okay, seeing it everywhere from flower petals right down to our DNA, it really makes you ask, is this all just a massive, incredible coincidence? Or is there some deeper, maybe simpler reason why this pattern keeps showing up?
That is the million-dollar question, isn't it? And it really pushes us towards some fascinating, more recent research trying to understand if this ratio plays a role in, say, evolution itself.
Ooh, tell us about that. That sounds like getting closer to a why.
Well, there was this really interesting study done by researchers at Johns Hopkins. They looked at skull dimensions in mammals. They compared about 100 human skulls to around 70 skulls from 6 other mammal species dogs, a couple of types of monkeys, rabbits, lions, tigers, a good range.
Okay, what were they measuring?
They focused on a specific curved line over the top of the skull called the Nazioniak arc. Basically, tracing the midline from the bit between your eyes over the top of your head to the bump at the back where your skull meets your neck. Then they looked at how this arc is divided by a point called bregma, which is roughly the soft spot on a baby's head, kind of the top center point. This divides the arc into a front part and a back part.
Right, so they're looking at the proportions of the skull curve. What did they find in humans versus the others?
This is the fascinating part. In humans, they looked at 2 specific ratios based on these arc measurements. The ratio of the whole arc to the back part and the ratio of the back part to the front part. And what they found was that in humans, these 2 ratios were essentially identical. They measured about 1.64 plus or minus a tiny bit and 1.57 plus or minus a bit more, both incredibly close to phi, 1.6 and an 8.
Identical ratios and both hovering right around phi.
Yeah.
That sounds significant.
It really does. Now, contrast that with the other 6 mammals they studied. In those animals, those 2 ratios were, first, different from each other, and second, the specific values were unique to each species. But here's the kicker. They noticed a trend. If you looked at the difference between those 2 ratios, that difference got smaller and smaller. It approached 0, meaning the ratios were converging towards phi as the species complexity, particularly brain complexity, increased.
So, like, rabbits had a big difference between the ratios.
Exactly. The rabbits' difference was about 1.44, but humans at the top of that complexity scale in their sample had the smallest difference, just 0.07. The ratios had almost completely converged towards phi.
Wow, so the study is suggesting
What?
that the golden ratio is somehow linked to the evolution of our skulls, maybe tied to our big brains.
That's precisely the hypothesis they put forward. It suggests this principle, seen elsewhere in biology, might actually be embedded in the architecture and evolution of the human skull itself, perhaps reflecting some kind of structural or functional optimization related to the expansion of our brains, especially the frontal lobes, over evolutionary time.
Okay, that adds a whole new layer. But it still brings us back to that question, why? Why this ratio? Is it some kind of mystical blueprint, or is it just math, physics, the easiest way for things to grow?
Well, many scientists lean towards the arguments of efficiency and simplicity. Nature tends to find elegant, economical solutions. Encoding a spiral growth pattern, for example, might be simpler genetically than specifying every point. It could just be a basic rule. Grow forward, turn by a specific angle related to phi. It's like a path of least resistance.
But optimization again, like getting the most leaves in the sun or packing seeds tightly.
Exactly. In many biological settings, these patterns are just highly optimized for resource capture or packing density. It often comes down to recursive processes, growth, that builds upon itself in repeating ways. And mathematically, the golden ratio often just naturally emerges from those kinds of efficient, self-similar growth algorithms.
It makes sense, but, you hear these claims, and sometimes, well, the saying, don't believe everything you read, comes to mind. Are all these examples really perfect golden ratios?
That is a really crucial point, and it's where we need to be a bit critical. A very common example, often presented as fact, is the nautilus shell being a perfect golden spiral.
Right, I've definitely heard that one.
Yeah, it's everywhere. But actual scientific measurements, like studies by Clement Falbo and John Sharp, have shown that while nautilus shells are beautiful logarithmic spirals, their growth ratios typically fall somewhere between 1.24 and 1.43, not precisely 1.618.
So close, but not quite fit.
Exactly. It illustrates something called confirmation bias. Sometimes we're so keen to see a pattern that we might overemphasize the examples that fit, or maybe slightly fudge the measurements, consciously or unconsciously.
So it's more about a tendency towards these efficient patterns, maybe, rather than every single instance being mathematically perfect.
I think that's a much more accurate way to look at it, even if it's not always exact down to the last decimal place. The tendency for nature to utilize these efficient, often recursively defined growth patterns is undeniable. It's the underlying mathematical elegance and the principle of efficiency that's really profound, not necessarily a rigid, universal adherence to the exact number 1.618 in every single case.
That makes sense. It's the principle, not just the number.
Mm-hmm.
Okay, but this leads us somewhere else too, because humans haven't just observed these patterns, have they? We seem to have felt something deeper in them. Some of the sources hint at a connection to consciousness, even something sacred.
Yes, and that takes us into a fascinating, though perhaps more speculative dimension. Ideas explored in works like Writing the Numbers, Ratios and Resonant States of Consciousness suggest that maybe our bodies, our whole beings, act like tuning forks. The hypothesis is that we might be capable of achieving a kind of attunement or resonance with these fundamental ratios found in nature and the cosmos, and that achieving this resonant state could lead to experiences of deep connection, maybe what some traditions call bliss, or even states of quantum coherence, a kind of optimal energetic alignment.
Resonance, like a musical instrument vibrating in harmony. It's a powerful image. Does this connect to older traditions?
Absolutely. Think about ancient practices like theurgy, which involved rituals aimed at connecting with divine energies. Part of that was about recognizing numinous tokens or signatures, these meaningful patterns in nature. Or consider gematria, the ancient system in Hebrew, Greek, and Sanskrit, where letters have numerical values. The idea was that certain words, names, or ratios between them, like the Christ to Jesus name ratio, sometimes cited as 1480 to 888, which is close to 5.3, another Fibonacci relationship could hold special resonances or meanings.
So it's this blend of math, symbolism, and maybe spiritual experience.
It seems to be. And it's not just ancient history. Think of the brilliant Indian mathematician Srinivasa Ramanujan. He was known for his incredibly deep, almost intuitive mathematical insights. He himself attributed many of his complex equations to visions he received in states he described as being like quantum coherent resonance. He famously said something like, "An equation for me has no meaning unless it expresses a thought of God."
Wow. So maybe these ratios aren't just about physical structure, but about how we perceive and perhaps even experience harmony itself.
It opens that possibility, doesn't it? Looking at it more broadly, you could see symmetry representing stable order and fractality representing self-organization from chaos, infinite complexity as two fundamental forces. They seem like opposites, but maybe they actually complement each other in creating the beauty we see. And perhaps the golden ratio often acts as this elegant bridge, linking the predictable with the infinitely complex, showing up in both the ordered and the seemingly chaotic parts of our universe.
So, okay, wrapping this all up, what does this journey mean? We've gone from defining the single number phi to seeing it pop up in flowers, shells, galaxies, even our own skulls. We've looked at why efficiency, simple growth rules, and touched on these deeper, almost mystical connections.
I think the takeaway is that the golden ratio isn't just some abstract curiosity for mathematicians. It seems to be a truly profound constant, maybe a quiet whisper of the universe's inherent design principles. It speaks to efficiency, yes, but also to a deep-seated harmony that connects things across vastly different scales, from a tiny seed to a swirling galaxy, and maybe even to the very structure of our thoughts and consciousness. It reminds us that beauty at its core can be deeply mathematical, this beautiful blend of stable order and the dynamic, self-organizing complexity of nature.
It really does feel like we've unveiled a kind of blueprint for beauty, doesn't it? A harmony that resonates through so much of existence. It definitely invites you, listening now, to maybe look at the world with fresh eyes, to start noticing the elegant math woven into the fabric of things all around you. What surprising patterns will you start seeing in your own world today? And before you go, please remember, this is just one of many fascinating deep dives brought to you by the All Sorts podcast. We're truly dedicated to transforming complex topics into engaging conversations that hopefully spark your curiosity and deepen your understanding of this amazing world. If you enjoyed what you heard today, if it made you look at a sunflower a little differently, please take just a moment to like this deep dive. Share it with someone else who gets excited about these kinds of ideas. And definitely subscribe to the All Sorts podcast on YouTube. Your support is incredible. It genuinely fuels these explorations, and we are so grateful to everyone who's already part of our community. You can also connect with us, find more insights, and join the conversation by following us on X, Instagram, and Threads. Keep exploring, keep learning, and please keep asking those deep, beautiful questions.